Okay, yeah. And then for problem four, okay, does anyone else have any other answers for this one? It's still the same substitution method. Oh, okay. So we have y equals to 13 plus 5t, 13 plus 5. Well, first of all, t, you know that t can be written as 12 minus x when you change this equation around. So t is equal to 12 minus x, and that is equal to 73 minus 5x. Okay. Yeah, negative 5x plus 73. So that's the answer like to this one. So this is roughly how sometimes you can turn some simple parametric equations into just like regular equations of y in terms of x. All right, next. Oh wait, that was a hint. Okay. So next, Kennan will be presenting this one.
Alright, so let's see this. Uh, maybe, so first I'll give you some time to solve it, I think.
It would be something like x is equal to like 5t and then y is equal to like negative 3t plus 1.
Yes, that sounds correct.
I'll just talk about it. So first of all, we have an ant. So it starts at like a point of 0, 1, and then it moves right with the velocity of 5 meters per second and a downward velocity of a 3 meters per second. Yeah. So anyways, so let's see. Okay, and then we model this with parametric equations. So first, we use a third variable. Let's say a t. So t is let's say like time in seconds since it started. Oh, time. Okay. So anyways, we have a note that x oh sorry, wait. Sorry. It's over here. Wait. So we have x as x starts from 0, right? As it moves rightwards with the velocity of 5 meters per second, this would be 5t because like t is the time and it moves with a velocity of 5 meters per second. So obviously x equals 5t. Oh, wait. And then we also know similarly that y, well, since y starts at 1, but it moves downwards. So we should have a subtract 3t. So basically this is the answer, I think, to this problem.
Yep, okay. Then we will go on to the next problem. This one is going to be trigonometric, and Justin will present this one.
Um, oh yeah, okay. So try to work on this for maybe like 1 or 2 minutes, and then we can go over the solution. Okay, so our goal is to write this in terms of x and y, so we should try to eliminate t. Okay, so if you look here, we have a cosine 2t and a sine 2t. And if you recall, we have the trigonometric identity, sine squared of 2t plus cosine squared of 2t equals 1 for any angle 2t, which means we can now substitute like in terms of x and y. So this is sine 2t will be negative y over 3 squared plus x over 3 squared equals 1. And this is x squared, this is y squared over 9 plus x squared over 9 equals 1, which rearranges to x squared plus y squared equals 9. And if you remember, this is the graph of a circle centered at the origin with a radius of 3. So that's how you do it.
Okay, okay, great. Then we go to the next slide. Okay. Okay, for this next slide, Justin will quickly do a recap of polar equations.
Okay, so we covered this in the last class. So polar equations are like you can express a point in terms of a distance r and an angle theta. So for example, r equals 3 would represent all points that are a distance of 3 away from the origin, which is a circle of radius 3. And you should also remember we found r cosine theta equals x and r sine theta equals y in the last class. So this will probably help going forward, so you should try to remember that. Yeah, I think that's good.
Yeah, okay. So then let's go to the next one. So here are some examples of polar equations. And now so just turn them into parametric equations of x and y in terms of theta. As a reminder from last class, we had x equals to all cosine theta, y equals to all sine theta. So if you guys have any ideas on how to do these, you can just send them to me. Yeah, so basically, when I say write it in parametric equations of x and y in terms of theta, it just means I want to write x in terms of theta, so like x as some function of theta and y also as some function of theta. Does anyone have some idea about how to do this?
I mean, I managed to convert the equation into rectangular form. It's like x squared plus y minus 1 squared is equal to 1.
Okay, wait. So actually, I mean that it is a circle, yeah, that could work, but the point of this question was actually to convert x and y in terms of theta. So even though you do have a relationship between x and y that isn't exactly what the problem asks for, but still that's very good that you got that one. Okay, so for this one, actually, let's just do this dumb and simple. So x equals to all cosine theta is equal to 2 sine theta times cosine theta. You can leave it like this, or you could also write this as sine 2 theta. This is the trigonometric identity, which I think has been gone over in week 1 and week 2. And y is equal to all sine theta, 2 sine squared theta. 2 sine squared theta, you could also choose to write that as
Like 2 minus cosine squared theta.
1 minus
Minus 2 cosine squared theta. Or like 1 minus cosine.
Yeah, you can also write as 1 minus cosine 2 theta because cosine 2 theta is equal to 2 cosine squared theta minus 1 equals to 1 minus 2 sine squared theta. So yeah, so you could just write like this. And this is basically how you do it. And then, well, I mean, once you have this, it also becomes clear that this is now a circle centered around the point 0, 1. Because look, sine 2 theta, cosine 2 theta is basically just a circle around here. Yeah. Okay. How about the next question? All equals to cosine theta. First, write it as x and y in terms of theta. So does anyone have the formula of x and y in terms of theta yet?
Yeah, so x is equal to like cosine squared theta, y is equal to 1/2 of sine of 2 theta.
Yes, basically cosine theta times sine theta because this is equal to all times of sine theta. And this is equal to all times of cosine theta. So yeah, very good. So this is equal to 1/2 sine 2 theta. And this, well, you could also write it as cosine 2 theta plus 1 over 2. Okay. So over here you see so basically the xy, if you look at it, this is actually equal to the point 1/2 0 plus 1/2 of cosine 2 theta sine 2 theta, which makes you realize that it's actually just a circle of radius 1/2 centered around the point 1/2 0. Yep. Okay, next. So next, Kennan will present this one.
Right. So I'll give you a few minutes to do this. Type in the chat if you. I haven't gotten any answers yet, so I'll just explain this then. So first we have we need to convert the following a polar equation to parametric equations in terms of x and y. I mean of x and y in terms of theta, and this is our polar equation. So anyways, remember first of all, we had x equals r cosine theta. Y. I'll just type from now on then. y equals r sine theta. Y equals r times sine theta also. So then let's substitute this equation. So first of all, wait, why isn't this working? Wait. Like, so let's substitute the expression we have right now. So into the formula. So first of all, we have x equals first of all, wait, hold on. First of all, we know that r equals a 2 over 1 plus cosine theta here. So so we can plug this into the equation. So this gives us uh, two cosine of theta divided by 1 plus cosine theta. Wait, hold on. Here. So this is what we get by plugging it in. And similarly, we can also plug in the expression of r into y. So this also gives us, wait, hold on, let me move this. Y also equals 2, also equals sine of theta over a 1 plus cosine of theta. Oh wait, it should show up. So this is what we get, and basically, hold on, let me check. Yeah, I think this is correct. So basically, this is our parametric equations for x and y in terms of theta.
Yep. Okay. And yeah, so this is what x and y looks like in terms of theta. If you want to find the relationship between x and y, we already went over that last class. To get that, what you would do instead is you would do r plus r cosine theta, which is x equals to 2. Then r squared is equal to 2 minus x squared. But r squared is, remember, equal to x squared plus y squared. So that's what you would do if you want to get the equation of x and y. Okay. Okay, so next we will talk about these polar equations.
You can take like a couple minutes for this. Okay, so for this first one, remember we have x equals r cosine theta, which is, if we substitute this for r, this equals cosine theta times 3 plus 2 sine theta. Okay, so if you want, you could expand that to 3 cosine theta plus 2 sine theta cosine theta. And similarly for y, we have r equals sine theta, which is sine theta times 3 plus 2 sine theta. Okay, for the second one, I'll go up here since there's not a lot of space. So r, this is okay. So for the second one, we have y equals r sine theta, which is 1 over sine theta times sine theta, which is 1, and x equals r cosine theta, which is cosine theta over sine theta, and that's equal to cotangent of theta. Okay, so we noticed that y is constant and equal to 1, and since cotangent of theta can be any real number, we have, so this is the equation of y equals 1, which is a straight line.
Okay, so then now we move on to the next slide. It's going to be about ellipses. So it's a new concept. Actually, so conic sections consist of ellipses as well as circles and also hyperbolas. For hyperbolas, we will get into that in the last week of class. So we don't have time. Well, Kennan defines ellipses.
All right. So first of all, ellipse, as it says, is a conic section. So basically, like as shown in over here, like if we have two cones shown together, and if we had a tilted plane, wait upon. And yeah, and actually, this cone in this shape, the hourglass. So basically the definition of the ellipse is this area here. But another definition is also the locus of all points where the sum of the distances. So for this distance and like this distance, a sum is like a constant, which is usually the major axis. So yeah, and then yeah. Then also the equation of an ellipse is x minus h squared x minus h squared over a squared plus y minus k squared, so on and so forth. Where note this means we have hk as the center. Wait, hold on. Hk is the center. And then also note that a squared, b squared, oh wait. Yeah. So also note that, like, for example, if suppose like this is our equation for the ellipse, then this would mean what? This would mean this is HK. H K. And then also a note, this would mean assume like we have note that the y coordinate is k, then that would mean we'd have this as h plus a. Well, okay, and then this part is h minus a. H minus a k. And then similarly for these two. So usually we take the major axis is the is whichever of the maximum of A, and B. And that's where the two foci are on. And then also consider its polar form. Its polar form is wait, hold on, let me erase this first. Its polar form is r equals divided by 1 plus e cosine theta. So also if you note that, for example, like if we have wait oh yeah, I see. But anyways, this is the polar form of ellipse.
Oh, yeah. And if you want to see how the polar form is related to the rectangular form, oh yeah, and this is an ellipse centered around the 0, 0. Okay, so but if you want to see how it's related, we can just apply what we did last class. First of all, this becomes r plus r times e times cosine theta. Oh, and e represents eccentricity or eccentricity. Yeah, I think it's eccentricity, right? Okay. But either way, e is a constant, and it is like sort of unique to each ellipse. It basically tells you like how curved it is and curved in which direction. But if you first multiply by 1 plus e cosine theta on both sides, this becomes r plus e times r times cosine theta. R times cosine theta is just x, and this is going to be equal to ed. Then r is equal to e times d minus x. Then you know what to do after this. You square it, so r squared becomes x squared plus y squared equals to e squared times x squared minus 2dx plus d squared. Yeah. And then after this, you notice that it becomes of the form something like ax squared plus by squared plus something something. And either way, yeah, this is just going to be an ellipse. Because you can directly complete the square. Like usually any thing of the form ax squared plus by squared plus some linear terms, that's an ellipse. And anything of the form ax squared minus by squared plus some linear and constant terms, that would be a hyperbola, which we'll talk about in the like last week of class. Yeah, okay. So practice. Okay, so Justin will show you some like practice exercises and like how to get like certain special points of the ellipse.
Feel free to work on this and send us your answers if you get them. Okay, so let's start with the first one. Over here. Okay, so I think Kennan already covered this on the previous slide. So the center is going that, well, you can see the ellipse is symmetric about x equals h and y equals k. So that means the center has to be at h comma k. I'll draw this here. So this is, then it'll look something like this. Okay. Okay, so let's start with the left and rightmost points. So the leftmost point of the ellipse is still going to have a y coordinate of k. So if we plug that into here, we get, well, when y is k, this term disappears. So we have x minus h squared over a squared equals 1, which means x minus h is plus minus a, or x equals h plus minus a. And since y is k, that means the left and rightmost points are h plus minus a comma k. Okay, so those are these points. And similarly for the bottom and uppermost points, the x coordinate will be h. So in that case, so it'll be this term that goes away, the first term. So we have y minus k squared over b squared equals 1, which means y minus k is plus minus b, or y equals k plus minus b. So it's similar to the x case. So this gives you h and k plus minus b. Yeah.
Yeah. So that's how you find the sort of endpoints of the ellipses. Okay, so I'll do, yeah. This is just a quick recap of what the first part is just a quick recap of what Justin just said. Okay, and now let's quickly get into what exactly is semi-major and what is semi-minor. So you know how as we just showed, the ellipse has two axes. This one has length, this axis has length 2a. This axis has length 2b. So the major axis is equal to the longer axis. The minor axis, as the name implies, is the shorter one. And then, so what about semi-major and semi-minor? So as you can imagine, the prefix semi means 1/2, right? So semi-major just means 1/2 of the major axis. Semi-minor just means 1/2 of the minor axis. Okay. So here, let's talk about the okay, Alexander, that is close, but we were talking about semi-major, not major. It's just semi-major length. Okay. So how about actually let's just do something more general. Let's just talk about this one. What are the lengths of the major axis and the minor? Okay, yeah, that answer is not correct. Okay. How about for this one? Tell me what are the lengths of the major axis and the minor axis using what we just got, or actually just using these. 2a and 2b, but which one is major and which one's okay? Yeah, I think actually we already have it. So
Yeah, but we don't know which one is longer.
yeah, basically as in you take the max to be the major and the smaller one. Yeah, okay. So as we said earlier, as like it literally follows from here. The horizontal axis is length 2a, the vertical axis is length 2b. So thus our two axes have length 2a and 2b. How do we know which one is major, like where the foci lie on? The major axis is just the longer one. So it's going to be the length of the major axis is the maximum of 2a, 2b. So that's the major axis. And the minimum of 2a and 2b, that one's just going to be the minor axis. Yep. And then as for semi-major, if we talk about semi-major, then it would just be 1/2 of that, which is just a and b. Okay. Okay, so let's go back to this problem then. So then what are the two axis length and like what's the semi-major length? What is the semi-minor? Does anyone else have answers? Okay, how about we first, let's see. Oh, okay, yeah, someone else has answers. Okay, it looks right. Oh, okay, wait. Yeah, Andrew, you're actually close. I think you may have mixed semi-major and semi-minor, but I'll explain in a moment. So actually, so what is the major axis length? Wait, actually, let's first talk about it. Let's first clear it all. So what are the two axes? The two axes, because x squared over 4, y squared over 9, what does this look like? It looks ranges from -2 to 2, -3 to 3, and it looks like this. So your two axes actually have lengths 4 and 6. Then which one is major? This one is obviously major because it's bigger. This one is minor. Then semi-major is equal to 3 because it's 1/2 of the major. And semi-minor is equal to 2. Yeah. Okay. Yeah, no worries. Yeah, sometimes people make a mistake. Yeah. Yeah. Okay. So then we'll go on to the next one, next concept. Yeah. Okay, so Kennan will do this concept.
Okay, so more about ellipses. So so as we had, this is the equation for ellipse, and then okay, hold on, hold on, let me check. Okay, never mind.
Yeah, it is.
Alright, so we have the major axis is the longer axis, and the short axis is the wait, uh, the short what's happening? Okay, and the short axis is called the minor axis. And then wait, why is this? Okay, and then the semi-major length is 1/2 of the major axis, and the minor length is 1/2 of the minor axis. Wait, Alex, did you talk about this slide? I'm not sure. Wait, Alex, did you flip the slide?
Yeah, no, we just talked about this in previous one. This is just a recap.
Oh, okay. All right. So anyways, yeah. So, as Alex said, the major length is 1/2 of the major axis, which is the longest axis, over here, and then half of that is like this length. And then, the semi-minor axis is this length, 1/2 of the minor axis. The foci fall on the major axis, which is something I already said before. And then for the ellipse, as it said, whose center is at the origin. Uh, wait. Oh yeah. So if an ellipse is centered at the origin, we can calculate the foci. It's basically these. What? Wait, Alex, should I prove this?
Oh, yeah, we'll actually be proving that in a
All
couple.
right, got it.
Got it. Okay, so yeah. Okay, so I think it was Justin going to do the proof of this. So I'll just first quickly draw a graph. Now let's just talk about a ellipse centered at the origin. Like let's like use the original definition of what foci are. So like let's say if the foci are in negative C and C, remember the definition of the ellipse, the other alternative definition of ellipse. Locus of let's call the foci F1 and F2, okay? the locus of all points P such that PF1, the length of PF1 plus the length of PF2 is equal to some fixed constant. Let's call this A. Why not A? Yeah. Yeah.
Okay, so we're trying to find the location of the foci in an ellipse. Okay. Okay, so let's say the equation is x squared over a squared plus y squared over b squared equals 1 because it's centered at the origin. And the okay, we're gonna assume a is greater than b since that's how it appears in the diagram. And this is a distance c from the origin. Okay, so by the definition of the ellipse that Alex explained, if we pick any 2 points on the ellipse, the sum of the distances to the 2 foci will be the same. So let's first pick this point here. Actually, I'll do it on this side. Okay, so since this distance is a and this is c, let's call this P1. That means P1 F1 equals a minus c. And we also see that P1 F2 equals a plus c. So that implies
And the sum
A1.
is 2A.
Yeah.
Oh,
Okay, so
so since like it seems we've like repeated variables, I guess I'll like change this variable to like let's just call this D for now then.
okay. All right, so this means P1 F1 plus P1 F2 equals 2A, which is equal to D. All right. Okay, now let's consider a point that's on the y-axis. So like this point, P2. So now P2 F1 is equal to P2 F2, which is equal to, so wait, let me erase some of this. Okay, so this distance will be B since that's the semi-minor axis, and this is C. And since this is a right triangle, we can use the Pythagorean theorem. So it's equal to the square root of B squared plus C squared, which means P2 F1 plus P2 F2 equals 2 square root B squared plus C squared. Okay, and now since these two expressions are both equal to D, we can set them equal. So, okay. So that means 2A equals 2 square root B squared plus C squared, or A equals square root B squared plus C squared. So now if you square both sides and rearrange, that gives you C squared equals A squared minus B squared. Which means C equals root A squared minus B squared. And that gives you the coordinates of the foci when A is greater than B. And for A less than B, you can you can do something similar, and you get an expression that looks similar to that.
Yeah, if A less than B, then actually the foci are on the y-axis. Yeah, so but this is basically the proof of so given the equation of the ellipse, and then you know this fact about the foci, like how you try to derive where the foci are. And also a couple of slides later, we'll give another more intuitive proof of how to derive the equation of an ellipse just from that definition. Okay. Okay, so for now we'll just first have Justin lead you guys to do an example of a quick practice on how to find the foci of an ellipse.
Okay, so we have the formulas for you here. So try to find the coordinates of the foci.
Hey, yeah, that looks right. Okay, Alexander, that looks right. Andrew, you put the foci on the wrong axis actually. Because in this case, remember A is less than B, so the foci fall on the y-axis.
Okay. So okay, so first let's draw the graph to just see, like, so it's going to look like this. The minor axis is 4, major axis is 6, right? Okay. So since B is greater than A in this case, the foci will be on the y-axis here actually. So again, let's say their distance C. Okay, using this, we have C equals square root of the absolute value of A squared minus B squared, which is root of absolute value of 2 squared minus 3 squared, which is root 5. So that means they're root 5 above and below the origin, which gives the coordinates as 0, plus minus square root of 5. So yeah, you can just do that.
Okay, yes, and that's how you get the foci of the ellipse. Oh yeah, and now as promised, we're going to show how you would derive, how you would get this, how you would get this equation from here. Okay, let's go to the next slide. I'll write it out. Here, ellipse. Shoot, too small. Okay, thanks. Yeah, thanks. Okay. For now, we're just going to call the two foci, like foci position C and negative C. And yeah, that's O. We'll call this F1, F2. Remember the definition, it's PF1 plus PF2 equals to some constant. And this constant here, let's just call it 2A. We'll later prove that actually, well, this does correspond to an equation, but we'll later show why. So how would you go from this to finding an equation? First of all, distance. Distance can be done by
Distance formula, so we have like P to C and then P to negative C. You just calculate the two distances and you do a little bit of simplification, you're pretty much done.
yes. So the distance from P to C, this is x plus c squared plus y squared. Okay, I wrote too big. Yeah. And then the next one, this is going to be x minus c squared plus y squared. And this is going to be equal to 2a. Okay. So let's take a look at this. First of all, we could first move some things to one side and square. Y squared is equal to 2a minus square root x minus c squared plus y squared. So then why don't we just square both sides? Then this gives x plus c squared plus y squared is equal to 4a squared plus x minus c squared plus y squared minus 4a square root of x minus c squared plus y squared. So first of all, there are already some things that we can cancel out. We can cancel out the y squared and y squared on both sides. The x plus c squared and x minus c squared, it can actually mostly be canceled out because you note that it's just a difference of 4xc, right? Well, you guys know why, right? Because the x squared plus c squared things cancel out. So yeah, difference of 4xc. So minus 4a squared equals to negative 4a square root of x minus c squared plus y squared. Cancel out the term of 4. Then becomes xc minus a squared. And okay, actually, why don't we also divide by a? Then it becomes xc over a minus a squared is equal to x minus c squared plus y squared. Right, I just like squared everything. I divide by 4a and squared everything again. So now this is the equation we get. Shoot, I might need some more room. So xc over a minus a squared. Okay, so then at this point, let's just directly expand. X squared c squared over a squared minus 2xc plus a squared equals to x squared minus 2cx plus c squared plus y squared. Then, of course, we will start canceling out terms. The minus 2cx minus 2cx. Yeah. Oh, sorry. Why does it look like a denominator here? Shoot. Go back. Yeah. Okay. So we cancel out terms here, and then what we get is x squared times c squared minus a squared over a squared. Wait, actually, no. C is going to be less than a, so wrong direction. So it's going to be x squared times 1 minus c squared over a squared plus y squared is equal to a squared. Okay. And then at this point, what we can do is we then divide again. Wait, shoot, let me check. Yes. X plus c, x plus y squared equals to 44 plus x plus c squared equal to minus 4a plus c squared. Oh wait, see. Okay, actually I made a small mistake here. Sorry, last term. Yeah, when you move it to the side, oh yeah, there's still this term of c squared here. So now this is what it will look like. Okay, so that's why it looked weird initially. But now we divide by a squared minus c squared, so we get x squared over a squared plus y squared over a squared minus c squared is equal to 1. Okay, and do you still remember initially what we said the formula of an ellipse was? Initially we said it's x squared over a squared plus y squared over b squared equals to 1, right? Yeah, so actually we just we set let b squared be equal to a squared minus c squared. Then we have x squared plus a squared plus y squared over b squared equals to 1. And c squared equals to a squared minus b squared. Yeah, so this is also why the focus of the ellipse is at the point a squared minus b squared. So I hope you guys understand how we go from this initial definition of ellipse and how we derive the formula for the entire ellipse just based on the foci and the sum of distances. Yeah, this is for the case when the foci are on the horizontal axis. If they're on the vertical axis, you get something similar. Okay. So if there are no questions, then we will move on to the next slide. Okay, so Ken will show you how to we'll be going through a simple ellipse exercise here.
Alright, so let's see this how much time should I give you? I'll give you like I'll give you 2 minutes. Until 41. Probably enter oh oh on. Or enter in the chat. Hmm. Uh,
I think we can start going over the question. Oh. Okay, I think I saw quite a few correct answers from you guys. So basically, this question is x squared over 5 squared plus y squared over 3 squared is equal to 1. And well, thus you have square root 5 squared minus 3 squared equals to 4. And because the major axis is the x-axis, then yeah, it just looks like this, negative 4, 4. Okay, how about this one? Wait, or actually, how about this? Let's first have a break. This question is a bit more complicated. We'll have a 5-minute break right now, and you guys can like think about the question during the break. Okay, break is over. Let's start the next problem. Yeah, Andrew, that is, you got the center. But then after that you have to find the foci.
I'll just talk.
Okay.
Right. Wait, hold on, do. Okay. Right, so I think, all right, all right, I guess I'll just talk about this one. So first we need to determine the center and the foci. The center is relatively easy. It's just, no, like we have x minus 2y plus 3. So that center is 2, -3. Oh, now we know the center, and then now don't forget we know the foci. If okay, wait, actually I'll start here. First, we know 25 is the major axis, so it'll look more like this. Okay, and then we know that that's the major axis, so these are the foci. Okay, hold on, calculate. Yeah. So these are the so the foci are over here, and then well, first let's ignore the center first of all. Like let's say the center well unnecessarily, but like let's say the center is 0, 0, and then we'll transform it later. So first of all, we remember this the equation for the foci if b is greater than a. If b is greater than a, as b squared minus a squared square root. As wait, no, 0. B minus a squared square root, and 0 negative b squared minus a squared square root. Okay, and then now we know this. We know this is 3. This is -3. So then we, yeah. So then that gives us. Now that we transform it, we add the x by 2, subtract the y by 3. So 2, 0. Oh wait, this is 2, 0. Then this is 2, -6. And then I think this we should be done. So this, get this also. So this is the center. And this is foci. And I think we should be done.
Okay, so that is how we do this problem. Okay. So then here is another problem. It is also similar, generally same idea. Okay, Justin will go over this one.
Okay. So first, let's draw the diagram. Okay, so it's going to look like this. Okay, so the focus is at 0, 3, and one of the there's a vertex at 0, 5. So since the ellipse is centered at the origin, h is 0 and k is 0, so that means it'll be x squared over a squared plus y squared over b squared equals 1. But we know that the semi-major axis is 5 in this case, so that means b equals 5. So this becomes x squared over a squared plus y squared over 5 squared equals 1. Yeah, okay. So since c equals 3 and b equals 5, and we know that c squared equals b squared minus a squared, so that implies a squared equals b squared minus c squared, which is 16, which means a equals 4. So this is 4, and that means the standard, like the final equation will be, if you multiply the squares, you get x squared over 16 plus y squared over 25 equals 1. So that's the equation. Right.
Yeah, so that's how you get the equation of an ellipse if you have the center foci and vertex. Okay. Next we'll be going into 3D coordinates. Justin will present this one.
Okay, so we've mostly covered the two-dimensional plane so far, and in a 2D plane you can identify a point with x and y coordinates. So x is this distance and y is that distance. These are perpendicular. So now we introduce the three-dimensional plane, which is essentially the same idea except there is now a third dimension. So 4, 5, 6 would mean this point is directly above 4, 5, 0. This is still 4, this is 5, and this is 6. So it's pretty intuitive, but so yeah, not much to talk about.
Okay, then next. Okay, so next we will be doing some practice problems.
Okay. Yeah, I know. Okay, I'll wait, I guess. I'll wait like until 11:01. Wait, no. Never mind. Whatever time it is, 8:01. But anyways, all right, and send your answer to me. I didn't get any answers, so I'll just explain this. Okay. One should be relatively simple though. So, first one is if a point lies on the XY plane. Let me get a better. No, this doesn't work. Okay. So I guess I'll have to draw a plane. So suppose this is 3D space. Why? Wait. Oh, wait. Like, suppose this is 3D space, and then this is like X, a Y, and then C. Oh yeah, thanks. I'll just use Alexander's curve. But anyways, so suppose like this is a Y, this is Z, then wait, hey, where did the x-axis go? Okay, alright. But anyways, and this is x. Suppose we have a point on the xy plane, let's say like over here, then we know its z coordinate is obviously 0 because it's on xy. So yeah, that's the first one. Z equals 0. And then for the second one, I don't know. But anyways, for the second one, yes, it's possible. And you know what, I'll just yeah, so I'll still use this. So yes, the answer is yes, it's possible, and there's a example. For example, like over here, of course, if we have like the line connecting them, like if they have the same x and y coordinates, then we could just pick 2 points here, such that like if you connect them, the line is perpendicular to this xy plane. And then for the third one, give wait. Oh wait. For the third one. So suppose like it's 4 units away. Wait. Well, it never said what direction, so it could also be 4 units this way. This point is z equals 0. This point is a point on the xy plane. Then wait. Oh, wait, better. Then note this point over here would have a z equals 4. Oh, wait.
Yeah.
I'll just erase this. And then note the point on bottom would have a z equals -4.
Yeah.
So yeah, basically we're done, I think.
Okay. So next, let's talk about the distance formula. So 2D distance formula in a 2D plane, it looks like this. So you have x1, y1, x2, y2. Then the distance is square x1 minus x2 squared plus y1 minus y2 squared. So this is for 2D plane. Then what about for the 3D plane? So I'll show you how to derive this. It can actually be done by applying Pythagorean twice. Suppose this is x1, y1, z1, and why don't we call this one x2, y2, z2? First of all, from x1, y1, z1, why don't we just take the plane that is parallel to we draw a plane through this parallel to the xy plane. So basically, okay, then from here we drop a perpendicular to that plane. So it looks like this. And we know that this height has distance z2 minus z1. Then what about this one? Can someone tell me what this length is?
This one, so like now we have like the point x2, y2, and then x pretty much like x1, y1. Shouldn't you use a 2D distance formula there?
Yeah, exactly. Because if you think about it, because if we just like compress it, like we project everything onto the xy plane, then everything's 2D and this distance is still preserved. So this length is actually just x1 minus x2 squared. plus y1 minus y2 squared. But then we have a right triangle, right? So we can actually just apply Pythagorean one more time. So we square this and plus z2 minus z1 squared and square root that, and we get this. Yeah, so that is how you derive the distance formula in the 3D plane. Yeah. Okay. And after this, we'll be doing a little practice. Yeah. Okay, so Justin will have you guys wait, oh wait, we just already did this. Yeah, never mind. Okay. Then next we'll be doing some distance formula practice. Like basically just find the distance between the two given points. Or find which one's closer to origin in the case of the second question. Yeah.
Oh, I guess, let's see. Oh no, I'll just wait like another minute. Bye. I'll start explaining, I guess. Let's see. I got one answer. Let me check that. Yes, I think that's correct. So basically, for the first one, the answer is 3 root 10. I'll explain that. Wait, okay, so anyways, this should be the correct answer. So I'll explain why, and then I'll just erase this graph. So suppose like we have the XYZ space, a 3D space, and then we have like okay, I'm not gonna draw out actually. I'll just compute it. So we have -3, 4, 6, and then we have 4, -1, 2. 7. So then if we consider the difference in coordinates, we get a 7, 5, 4. Well, I mean, relatively speaking, because we're gonna square it anyways, so the sign doesn't matter. But anyways, this gives us 7 squared plus a 7 squared plus a 5 squared plus 4 squared. This gives us a 49 plus 25. Okay, and then so anyways, we can compute this, and then we get this, let's see, this is 16 plus 49, that's 65. So this is 90. So in the end, by using the distance formula, we get square root 90. A square root of 90 is 3 root 10. So yes, I think 3 root 10 should be correct. And I think Justin will talk about number 2.
Okay, so we have well, the origin is at 0, comma 0, comma 0. P is -3, 4, 12, and Q is 6, -8, -8. Okay, so let's call the origin O. Then well, instead of taking the square root, we can instead find OP squared, which will be equal to 3 squared plus 4 squared plus 12 squared. Wait, this is just distance formula, but with both sides squared. So this is 9 plus 16 plus 144, which is 169. And then OQ squared is 6 squared plus 8 squared plus 8 squared, which is 36 plus 64 plus 64, which is 164. Okay, that means OP squared is greater than OQ squared, which means OP is greater than OQ, which means Q is closer to the origin. Yeah.
So yeah, so that's how we do these two problems. Next we'll be doing some more inequalities, like distance formula inequalities. Okay. So if you guys have any ideas for these two questions, you can just type them to me. Does anyone here? Okay. Yes, we have one correct answer for number one. Okay, so I'll just go over this problem. So given that the coordinates of a point R are -4 to Z, so R is at most 14 units away from the origin. So -4 squared plus 2 squared plus Z squared is less than or equal to 14. So Z squared plus 20 is less than or equal to 196. What was the second one? Yes, that is correct. Okay, so Z squared is less than or equal to 176. Hence Z must be less than or equal to 4 root 11. It asks for the maximum possible value. So thus 4 root 11 is the maximum possible value. How about number two? Does anyone have any ideas? Does anyone else have any ideas? Like what shape does this expression look familiar? Like does this expression look familiar? For instance, if I took the square root of it, wait, so so I'll first write this out. Imagine if you did this. So then what does this mean? Wait, can someone tell me what this means? Remember the earlier distance formula? Let me quickly go back. Hey. The earlier distance formula was this, right? So can someone tell me then what does this mean now? This. Yeah, exactly. The distance from, I'll just write distance from XYZ to the point 3 to -4 is equal to 6. In other words, also if you imagine like all points with the same distance to a point, to some, like given a point, take all other points with distance 6 to it, then what is this? It's just a sphere, right? That's the definition of a sphere. So it's a sphere that is centered around the points 3 to -4, and it has a radius of length 6. Yeah. Okay. Then we will go on to the next question. Well, actually, next concept now. So Justin will present about planes.
Okay. So the definition of a plane is a flat two-dimensional surface that extends infinitely far in all directions. So like, uh, so for example, the XY plane would be like this. So that's one example. So actually, the general equation of a plane can be written as ax plus by plus cz plus d equals 0 for some constants a, b, c, d. And note, well, we know that the equation of a line in 2D can be written as ax plus by plus c equals 0. So this should like kind of make sense. I will prove this on the next slide. So most natural proofs of this use a normal vector, which is defined as a vector perpendicular to the given plane. And since we haven't covered vectors in this class yet, we'll just explain like the main idea, and you can like review later if you want to.
Sure. Now let's go on to the next.
All right.
Yeah.
Okay, so imagine like, okay, let's imagine this, we're given a plane, like kind of like this. Okay. And this is it's a vector perpendicular to the given plane. So vectors have components. So let's say the components of this one are a, b, c. Also, we have points p0. P0 is at x0, y0, x0, y0, z0, and p is at x, y, z. Okay, so we can find that this vector pointing from p0 to p has it has components of x minus x0, y minus y0, and z minus z0. And later we'll cover something called the dot product. So what you need to know for now is that if two vectors are perpendicular, then their dot product is 0. Okay. So since we haven't covered that yet, I'll just say that if you carry out this computation, you'll find that it gives you ax plus by. Well, since these are perpendicular, well, this will be equal to ax0 plus by0 plus c0, and this is a constant which we can call negative d. And if you rearrange, that gives you ax plus by plus cz plus d equals 0. So that's the idea.
Yeah. So yeah, this concept, we can later go over it after you guys have learned about vectors. I think that'll be like in maybe 1 or 2 classes. Then next. Okay, so equation of a plane practice problems. If you guys have answers, then you can just type them to me and Kennan and Justin.
Alright. I guess there are no answers, so I'll just start talking about this one. So the first one, so look at this. We have x, y, y, z, and x, z planes. Well, note the x, y plane is just z equals 0. The y, z plane is x equals 0. The x, z plane is y equals 0. And then for the general, why isn't it? Like, for the general plane equation, wait. Wait, where's my cursor? Oh, so basically, if we plug it in, so first of all, wait, something went wrong. Wait, oh, wait, oh, here we go. Wait, what is it? Wait, so we note the general plane equation is ax plus by plus cz d equals a 0. Oh, and then note that like all of these, for example, let's say z equals 0, you could just like a equals 0, b equals 0, c equals 1, and d equals 0. And for example, like let's say x equals 0, we can just do a 1, 0. 0. Anyways, you can see by assigning some coefficients, we can let the variable we want to be 1, that coefficient, and then all the rest to be 0, and that's how we know it matches with the general plane equation.
Yeah. Okay. And so for the next one, find the equation of the plane passing through the points. Okay. In this case, remember, so ax plus by, this is the general equation. So for this one, since it passes through all three of these points, well, it actually equals to some d. Okay, let's first talk about this one. We have 4a plus 0b plus 0c, or just in other words, 4a equals to d. The second one, ax, well, x is 0, y is 2, so 2b equals to d. And then this one, now cz is also equal to d. So this one is going to be c equals to d. Oh, wait, you guys understand why the other terms are gone, right? Okay. So either way, I hope you understand this one. So like, it's just because these are zeros. So now you have 4a is equal to d, 2b is equal to d, and c is also equal to d. Okay. So then after this, we basically just have to solve, although this alone is not enough. So how about we instead replace, or actually, why don't we set some other constant? Let's write everything in terms of a. If we do this, then b is equal to 2a, c is equal to 4a, and well, also d equals to 4a. And as for, well, a is just a is itself. So in other words, the equation of the plane is now ax plus 2a times y plus 4a times z is equal to 4a. And wait, so you see you can actually simplify it. Okay, someone else answered. Yeah, that is correct. Okay. So, and now you see you can actually simplify it because a divides everything. So cancel out a. Then you get x plus 2y plus 4z minus 4 equals to 0. And this basically now gets you the equation of the plane which passes through these points, and like you can verify that this works. Yeah. And then the next question will be about how to determine a unique plane, like how many distinct points you would need. Okay. So if you have the answer to question 3, just chat it to one of us.
Okay. So, okay, so how many non-collinear points are needed to determine a unique plane? So, let's draw the 3D plane here. X, Y, Z. Okay. So first, let's see if 1 point works. Well, of course, 1 point doesn't work, since if you take this one here, you could have like this, or well, there's infinitely many planes passing through 1 point, basically. So 1 is not sufficient. And similarly, for 2, 2 points determine a line, but you can still have infinitely many planes by just taking one and rotating it about this line. So that also doesn't work. But for 3, okay, so since the points are non-collinear, these will determine like a triangle. And now if you extend the triangle in all directions, this gives you the plane of the triangle. So actually 3 is enough. And you do need the points to be non-collinear, because if they are collinear, then this will just form a line, and again, there's infinitely many planes. You can also see this from the plane equation. So if you have 3 variables, you need at least 3 different equations to solve for, well, up to scaling. So yeah.
Okay. Yeah, okay, so basically 3 points determines a plane, and yeah. Okay, then now, so basically the class has ended. So we've gone over many important concepts today, including ellipses, 3D coordinates, and all of that. We have quite some practice problems here. First of all, there's a Precalculus enhanced, and then the bonus from AOPS, from the AOPS Precalc textbook as well. Our office hours will be held on Saturday, and we'll also post the answer key on Saturday. Yeah. So if you have like any questions about the homework, like we highly encourage you to come attend our office hours. So like you can ask us the questions and we will go over them. Yeah. The class recording will also be posted right after class.